Okay, thanks for coming back, everybody. Up next, we have Bruce Fuda. So Bruce is now a computing education specialist at the Australian Computing Academy, which we heard about this morning. But prior to that, Bruce was acting as associate principal of Gungahlin College, a government school of around 1,200 students in year 11 and 12. And he was a writer on the Australian Curriculum Technologies, and has been involved in projects across multiple Australian jurisdictions, developing teacher capability and lesson resources to support the implementation of the curriculum. And he's here today to talk to us about introducing students to object-oriented programming. Thank you, Bruce.
Thanks, Nick. Okay, so what I thought I'd do today is I'd begin by giving a very quick overview of where things are in terms of the curriculum. Amanda's talked a little bit about that, so I won't spend too much time there. Then I'm going to run you through the example we use in the classroom that we find is very accessible to students, and I'll give you a quick look at some student work, and I made sure that there's time for questions, because I think this is a topic that some teachers find very challenging to introduce students to, and I'm going to try to give you a strategy for making it accessible. So a little bit more about me. Nick's covered the big stuff, but basically I've been teaching in schools for about 13 years. I've worked with students primarily from year 6 up through to year 12, and teaching year 9 through to 12 has involved teaching OO a lot of times. So I've done it a little bit. Like my intro said, I was involved in the writing of the Australian curriculum, and I also do a little bit of development on the side. Most of that is in the web space, and it's to deal with systems in schools that are rubbish, which if you're a teacher, I'm sure you encounter on a daily basis. So I use what I know to work around that. So a bit about the curriculum. And I want to start by just emphasising once again the concepts that Amanda referred to in her keynote. The curriculum does something very different to what other curriculum areas do in the Australian curriculum, in that it is all built on 10 key concepts that have been and will continue to be true in computer science information systems. And that was intentional. You can't design a curriculum in a learning area that changes so rapidly. 15 years ago, we didn't have the iPhone. We didn't have a lot of the services that we rely on daily now. And given that the first students that do this curriculum officially around the country won't be in the workforce till 2036, and the curriculum was designed in 2010, that's basically dinosaurs running around on the planet in terms of where things go. So what I'm going to focus on are 2 of these concepts. But before I do that, I think I'm going to be a little bit more generous than Amanda was this morning. I'm going to give an indication of where different jurisdictions around the country have committed to assessing this curriculum. The good thing about Victoria is you're sort of doing it already, and WA have committed, and Queensland have all committed to be assessing this right now in 2017. In 2018, we'll see most of the country reporting on the curriculum formally. But last year I gave a presentation and used a similar map like this to highlight that big gap in the middle. We're pretty confident that by 2019 New South Wales will be reporting on this too. So it is something that we're going to see every student in the country exposed to, and there are going to be challenges, particularly in the higher year levels, to introduce students to these concepts and ideas because they won't have the 11 or 10 years of prior experience when they do that. So as far as programming goes in the curriculum, there's a progression that I think is important to acknowledge and to be aware of. In Foundation to Year 2, the early years of schooling, there's actually no requirement for students to do any programming whatsoever. We introduce them to the idea of algorithms, and one of the best ways to introduce them to this idea and to the concepts of sequencing is through physical type activities. So getting them to provide instructions to someone else to follow to achieve something, or doing something very simple with a technology like the B-bot, which is basically a little robot that you direct to move around the floor with instructions like forward, back, and turn left and turn right. Those activities stress to students of sequencing and understanding what that is. As we move into the higher years of primary school, we introduce the idea that not only should you be able to follow an algorithm, but you need to be able to define a problem that an algorithm will solve, design that solution, and then implement it in code. And we do that in the primary school through visual programming environments. So Scratch is probably the example most people are familiar with, but it includes other things like Blockly, Alice, and a couple of other tools that generally get used quite extensively in schools already. This is not something that's unknown, but it is something that teachers, in many cases, haven't really had time or space in the curriculum to deliver on. So by the time they hit year 6, they're doing branching, they're doing iteration, and they're dealing with user input. And when we talk about user input in the curriculum, we mean both direct user input with keyboard and mouse, as well as environmental input. So the kinds of things that you would get through a light sensor in robotics. Now, when you hit year 7 and 8, that's when we introduce the text-based programming languages, and we want schools to select a programming language that is general purpose, not domain specific. And that's important because Foundation to Year 8 are the compulsory years of the digital technology subject in schools, and we want to equip students with a tool that will allow them to do things in other learning areas that they've never been able to do before. So it's very, very important that consideration is made when selecting a language. In addition to being able to define a problem, design a solution and implement it, we want students to start thinking about validation, and we want them to begin writing their code using functions. This idea of being able to reuse things and design things that are general enough in nature to be reused is the concept that gets introduced in year 7 and 8. And that's the end of compulsory digital technologies in school. So my focus today is on what is currently in the year 9 and 10 elective subject, and is often delivered at the moment in year 11 and 12 curriculum areas, if at all in schools. In many cases, it's not until university that students get introduced to these ideas. And when we're looking at object-oriented programming, in addition to that, we want students to be able to sort of distinguish between a program code that sits in a program and code that might live in an external module, as well as being able to test their code and design test cases that will give them confidence in the correctness of the implementation of their algorithm. Now, as far as the curriculum is concerned, programming isn't the only place that object-oriented concepts live. It's very important that data representation gets mentioned here as well, another critical concept that sits at the core of the curriculum, because one of the interesting things about the design process of the curriculum is that it was insisted that some things go above the line in the knowledge and understanding strand and others sit below in the processes and production skills. And traditionally, the knowledge strand has kind of been the stuff you need to know but don't actually need to do. It's like, the dates that World War II took place or who the Prime Minister is. You don't do anything with that knowledge, you just have to know it. But the interesting thing about our subject is the whole thing's been designed so that it's practical, that you're applying everything that you're doing. There is no knowledge that sits on its own. So although this is a knowledge element of the curriculum, one of the things we want to make sure students do is that they're using these ideas in practical contexts. And object-oriented programming is a really good opportunity to explore structured representation. And that's where year 9 and 10 is where that kicks in terms of the curriculum. So we're taking this idea that things can be represented in different ways, either as patterns or pictures, or understanding the difference between the types of data that exist, and we're taking it that little bit further to say that we can have these extremely complex things that we model in data, and that the structure is really, really important for us to be able to use that inside the programs that we write. So as far as OO is concerned, the writers were very specific about what needs to be included for the object-oriented element of the curriculum to be addressed. And I think it's really important that every time we design a project that uses OO, we make sure there are opportunities for students to explore these three things. They are user-defined classes. If they're not defining their own class, if they're only using classes that exist already, then they're not really being exposed to the power that an OO approach actually introduces in your applications. Secondly, the concept of inheritance is really, really important because it allows us to think about how we generalize things and how the representations that we use in our applications are designed in such a way that we can reuse code as much as possible. And finally, which sits with inheritance, is the concept of polymorphism. And again, that's got to do with how we make use of the different things that exist in our code to make the applications that we develop simple and easy to follow. So I want to clear something up very, very quickly, because this gets thrown around a lot when we deliver it with workshops with teachers. And that is, they say, well, Scratch uses objects everywhere, so I'm doing object-oriented programming. Now, it's true, Scratch has objects, but it's not object-oriented. And that's because while they're present, there are a number of things we can't do with the objects in Scratch. And so there is no way of defining your own class. Everything's a sprite or a background. And you can attach things to those, but you can't come up with some new data structure that allows you to do different things inside your program. The other thing is there's no concept of inheritance or polymorphism. There's a clone feature which allows you to make a copy of an object and retain its existing state, but it's not the same, right? I mean, you're basically creating a second object. You're not doing anything in any way that takes advantage of the benefits of inheritance or polymorphism. So what one of the great things about Python is that it's object-oriented, but it's also a language that we can introduce earlier on as a general purpose programming language in Year 7 and 8. So I think one of the benefits of Python, and the reason we use it extensively in our programming, is that it's very, very simple, it's very, very powerful, and it does everything we need to be able to address the curriculum expectations. So we have user-defined classes, and what I like about the way that classes are defined in Python is that students who have seen functions before have basically seen class definition. They're very similar in terms of their structure. Yep, there is a new keyword and the syntax is a little bit different, but if you know and understand how a function works, then to make the transition to classes is a relatively easy step. And it has those two concepts we were talking about before, inheritance and polymorphism. And what's really nice is that the way inheritance works is not crazy complicated. The idea of the original object almost being a parameter to the class is something that, again, is very, very similar to the way functions operate, and it's easy to communicate and describe that to students. So a little bit about the framework that we use at Gungahlin College and that I used at the previous school before that, Stromlo High, when I was teaching this, because I think it's really important that we understand what the thinking behind the approach is. Now, there are three elements to the way we deliver. The first is that we make sure that there are opportunities for the teacher to explicitly teach the ideas so that we can be confident that the students understand the concepts that they're going to be using in their various applications, because we want this to form the basis of their understanding so that they can use it in other learning areas as well, and projects beyond the digital technologies. In addition to that, we want students to be able to go as far as they want once they're on top of the foundations of OO. So we provide a lot of additional resources to students. I'm going to show you two of those that are specific to OO that we use in class. But primarily, the idea is that we want to make sure everything is open enough for students to be able to take what they've learned and go in any direction they like. And finally, we want to make sure that those projects that we set as far as assessment are concerned and that we do in class are as practical and engaging as possible for students. And we want to make sure that that same scope for exploration is present in the activities that they're doing for assessment as well as classwork, because it's going to keep them engaged and it's going to mean that there's more opportunity for students, regardless of where they're at, to be able to achieve something in terms of their output, their final product. So, how do we teach it? The first thing that I think we emphasize with students is that the idea of an object-oriented approach is to change the level of abstraction we're working with so that we have some way of modeling the objects that exist in the program in a similar way as we would model real-world objects. So everything that we put inside a class is describing something that is common to a group of things. The idea of a class being a sort of description that contains the common properties and the common behaviours and can be used as a blueprint for anything we create in a program is a very, very easy concept for students to understand if you give them something tangible in which they can see that apply. When you move from there into the object and you start talking about the differences between them, it's very easy in this particular case to be able to point to common examples in various realms that students know about. They understand the difference between two characters in a game or between two cars in a car yard that are the same make and model but can be moved and manipulated independently. So we can refer to them as being a group that shares some kind of common as I said before, property or behavior, but we can differentiate between each of them because they have a way of referring to each independently. So the example that we've used primarily in teaching this is that of an inventory system in a game. And that's intentional because we move from here into a project that has a significant game engine built into it. And so when they understand how an inventory works, it's one of the options they have to implement and extend the properties of that game. So let's say we're coming up with a pack. And normally in class, I would live code this as we go. So every time I do this, we get a slightly different version of things. I've just selected one that came up before. It's not the best example that we've ever produced in class, but it was one that we developed as a group. And I'm not going to live code it here because we end up adding a whole heap of extra bells and whistles that would just mean that we won't get through the presentation in the time we've got. So all packs have the ability to store things and they have a capacity. All right, if we were to sort of say what is the minimum set of requirements for a pack, we'd say that. And so these are the things that we'll use to define our class. But the thing is that not every pack is the same. We have packs of different sizes. We have packs that contain, that are made of different things, that are different colors. And so the differences in these are what have reflected in the details of the object. Okay, they're both packs, but this one here is blue and black, and that one over there is green and brown. That one's got more pockets. There are noticeable differences between the two, but they belong to the same group, the same class of things. So we would then walk through the process of developing a class definition, and we would explain to students, what we're doing each step of the way. So here's an example class for our pack. It's got some properties, the things that every pack has, and it's got its methods, the things that every pack does. So that distinction is relatively easy to explain to students. You can draw the relationship between functions and methods based on their understanding of what those are. And the idea of a property as being something that lives within the object's scope is something that also they'll be familiar with from their previous experience. So we take our class definition and we use it some way like this. And when we print that out, we get this output. And what does that look like in terms of the environment that the game is running in? Well, we have these three packs. Right? We've got a pack that has a capacity of 20, a larger pack with a capacity of 50, and then we've got our little pack, our tiny pack, which has a capacity of 5. So 3 distinct things. We can refer to each of them independently, but they all share the behavioural elements that we want to be present in our pack, in our game. So that's a really simple example of an object, but objects alone, right, they need some way of interacting with other things. So let's look at some items that we might put inside our pack. What do they have in common? Well, at a minimum, they've got a name and a size. And there are lots of different types of items, so it's a good example for exploring inheritance and polymorphism. Now, there's more variation in items than there are in packs, right? For example, these both have a size and a name, but we swing that and we eat that. And you definitely wouldn't do it the other way around. I mean, you could swing a steak, but it's probably not going to be very menacing, right? And some people swallow swords, but I don't think you'd count that as eating. So we have our base class, and that's going to be common regardless of any other weapon we create, any other item we create. And then we've got our weapons. Now, weapons inherit elements from the item class. And again, this is an example where we haven't exactly chosen the best example because we're primarily just inheriting the properties here. And then we're redefining the string representation. However, we have created this swing method that is unique to the weapon and didn't exist in the item. Now, in food, we've got a similar thing. We inherit all of the things that are in items, but we can eat food. And so we've defined that as well. Now, when we use these, it's important that we can see the distinction between weapons and foods. And the changes that we made to that print, to the string method, allow us to, when we run this code, see that the output differs. So we've created them using their constructors, we print them out, and we can see that swords have power, or because they're weapons and weapons have power, and steak has a potency, right? Its effect from eating that steak. So we now have 3 things. 2 of them have elements in common, but all 3 are items. And we see that all 3 are items through our exploration of polymorphism. So here's our pack. And what we've decided is that all items can go in the pack, regardless of their type. Right? You can pick up swords and you can put them in your pack. You can pick up steak and you can put it in your pack. So if it's not a weapon or food, it shouldn't go in the pack. So our sword can go in, right? Our saber can go in, our steak can go in. But if we try to put a string in, we want to make sure that that doesn't go in there, and we want to make sure that we don't let integers in there too, because they're not items. So we define our interactions in the superclass that we want to add all items. This is a pack, and in our pack, what we're going to do is we're going to come up with this kind of add item method that will allow us to add an item to the pack if it's allowed to be added, or will not add it if it's not. So at the moment, the way it's written, we're checking to see if it's a weapon, and if it is, it can go in, and if it's not, then it doesn't. Now, obviously, we want to put other things in the pack. So the naive implementation would be to add a check for food, and that'll allow the steak to go in. But then if we want to add something else, we need to keep adding more and more ors, and it becomes unwieldy. So we swap weapon out, we use our polymorphism to check whether it's an item of any kind, and that allows us to add anything that we classify as an item as we expand the number of types of items in our game. And one more time, this is what it would look like. You can see that we can't put the not an item string in our pack, and we also check to see whether or not we have room for items based on the other properties that we've developed. So they're the kinds of examples we'd run through in class with students, and that's the state of the program after that runs. So 2 really useful resources that we've found. I haven't found a good, simple explanation that sort of beats this one. Jess Hamrick actually presented at PyCon US, I think back in about 2013 or something on a different topic. And she's got a blog post that runs through a really simple example using pets and cats and dogs. And it's really, really easy for students to work through that. More generally, the How to Think Like a Computer Scientist resource is really good. It uses points and shapes as its example for inheritance, and it's not as sort of exciting for students, but it is quite clear in terms of its explanation. So I'm going to run through this really quickly, but I think it's important that you've got this in front of you so that you can see what we do. Now, as far as our task structure goes, we have the idea of students documenting and improving code and then extending and redefining it. And what that looks like is we provide an RPG battle engine that works, but is very limited in terms of what it does, and it includes no documentation whatsoever. So we start out by giving them their 4 files, the entry point, a GUI, a simple I/O that we've created, a battle class, and a character class, and altogether that's about 1,100 lines of code. And the idea is they interpret what everything is doing. There's a lot of repetition in there. It's not the best designed code in the world, but it's easy to read and understand, and that's the goal. So they document that. They then extend the functionality, and we give them a list of things that they can try to do that. So lots of different options designed to ensure that every student can achieve something, but we provide a sort of list of the harder things that we'd like top students to do. They can construct something that doesn't exist at all. They create a map class so that they can have some kind of world the character can interact with outside of the battles when they take place. And finally, for the highest performing students, we encourage them to refactor the existing code, to look at ways that they can make things that are a little bit easier to write, or a little bit more powerful and more efficient in terms of the way that they run. So I'm just going to finish up with a very 1-minute example of a couple of projects. This is sort of your basic, I've done everything that I needed to do and I've done it well example. It's a text-based adventure game. There are menus there that they have to think about in terms of when they're presented, how to interact, what appropriate options are. And you can see that's been extended with a sort of ASCII map down the bottom there. You can move around the map, and when you encounter an enemy somewhere on the map, then it launches our battle class. It instantiates a battle object and a battle occurs, and you just go through the process of, the battle actually happening, which is the code they're provided with initially when we start off. So that's a kind of simple but well-written example of a completed project. Now, this is what you could do if you're a little bit stronger. And this student got a little bit carried away, decided that he was going to interrogate the GUI class a little bit as well and work out how we could open multiple windows, not just work in the one. So you've got your starting point, you've got your map in the middle, you move around the map, you enter a dungeon, and now you've got a dungeon map that you walk around in. And then eventually, when you run into an enemy, not only do you have the battle taking place on the left, you've got real-time statistics sitting in the right-hand window. Okay, so all of this stuff is possible because we've provided enough flexibility for them to be to extend what they're doing. And I guess ultimately, one of the things that why we want this to be introduced to students is because OO is everywhere. It's in web frameworks. It's used in games. Database models rely on it, and any GUI work relies on OO as well. So it provides a level of abstraction that we need to be able to understand very complex applications. We can't write software that is very, very complicated without it. And so it's really, really important that students have an opportunity to explore OO in that context. So that's it from me. I've got a little bit of time for questions. Thank you.
Okay, yep. Hands up and I'll bring the mic around.
Thanks for your talk. With the add to pack method, there's extra work involved in dealing with the possibility of calling that with a number or a string.
Yep.
So you gave the example, we don't want to be able to add the string dog to a pack.
Yep.
So why aren't we using languages and tools that would allow the students to express the operations that make sense whilst not even admitting the possibility of someone attempting to add the string dog to a pack?
Right. So,
namely statically typed languages.
Yeah. So, I mean, really the reason that we use Python comes down to the fact that it's just easy to learn, right? The syntax is simple. It encourages good practice with indentation and all of the like. So, yes, we could switch languages. We could look at an option that would allow us to work in a more sort of statically typed language. But one of the things that I think we need to keep in mind as educators, especially if we've got a computer science background, is that if we expose students to many languages and we ask them to go back over those same concepts and relearn the new syntax and the intricacies of working in another language, they don't get the opportunity to dive into that language deeply. So is it more beneficial for a student to be able to write an if statement in 8 different languages, or is it more beneficial for a student to really know one language well so that they can write really interesting, complicated applications that make use of some of the other features in the language? So because we use Python for everything else in the lead up to it, we continue to use it, and in that example, we actually would explain to the, so we wouldn't put that as instance check in there initially. We would just start and then I'd throw the string in and it would go in and they'd be like, hang on, we're getting an error because it doesn't have a name or whatever. And then we'd talk about is instance and one of the things you need to factor in when you're designing something using Python. So it's more of a, what I think it does is it stresses to students the need to understand type, because you can't rely on the compiler picking it up for you in advance. And so, yeah, it's primarily because pedagogically it's better to dive into a language in detail than to learn lots of languages at a shallow level.
Hello, good talk. I just wanted to know, because I see a lot of people using inheritance where it's not needed. Is there any concept that the kids learn about class composition where a base class has something and not, do you know what I mean by that? You
mean when you say it has
Yeah, so maybe your pack would have a pocket and the pocket has its own functions.
Yeah. So
instead of inheritance.
I mean, because the concept is what we're trying to express here. We're not necessarily trying to model a perfect pack, right? And yes, we could go down that path. And in fact, some of the students that have designed more complicated applications, they do identify that. And so, you know, they might have, someone might introduce clothing as another item that you can have. That clothing can store things. That now has things in common with a pack. Hang on, wouldn't it make sense to create a pocket or some other item that we could then incorporate into those two objects? It can happen, but for students who are maybe seeing programming for the first time, this is something they do after having been programming for about 6 months. For students who have sort of come from nothing to that in 6 months' time, that's a layer of complexity that's just a step too far in terms of what is necessary. Yeah.
Any further questions? Okay, I'll ask one. So something we're looking at in the language design at the moment is a notion of data classes that basically get away from people having to define the dunder and knit and dunder str manually, and instead being able to just declare my class has these attributes.
Yep.
And have the language auto-define the dunders for you. Do you think that would actually help students? Or do you think it would be hiding too much magic and potentially make things harder to understand?
So, I mean, I think it could do both, depending on the student. But I don't, so the idea of sort of the constructor or these, you know, other reserved methods that live inside a class is not something that they struggle with too much. They see the value in having, for example, a way of defining str so that you can just print something out and you don't need some show pack method or something like that. So I think we could go either way. I think regardless of whether it exists or not, we can work around that. I don't think one of them is going to be inherently better for teaching. I think it's better to make that decision based on what the developer community needs in the real world rather than sort of worrying about what we do in school. That's something we can work with either way.
Cool, thank you.
So you mentioned, sorry, I've forgotten the terms. But basically, my question is, do you also teach encapsulation?
Yes, so we do. It's not specifically mentioned, but you kind of have to teach it anyway once you start diving into classes because it doesn't make sense to put things outside of the class if the class needs it. So as far as the curriculum is concerned, you won't actually see references to inheritance or polymorphism or anything in the curriculum document. And a lot of that is because a curriculum document is, you know, 12 dot points that need to be understood and interpreted. So I would say that you really can't teach it without it, but it's not something that you'll see anywhere. And I think it's important that when we do teach it, we use the terminology. It's actually one of the conscious decisions made by the curriculum writing team is to use the language of the discipline throughout. And that's been one of the big challenges at the same time because teachers without the background don't know what it means. But at the same time, we don't insist that maths remove the term sabotage or that, you know, science talk about the various things in the different fields of science without using their formal language. So if we could, I think it would have been great to see encapsulation, inheritance, polymorphism appear in the document itself. One place where it will appear is on the Australian Computing Academy website, the resources that we're putting together. We'll make sure there's reference to all of that sort of thing. And a review of the curriculum that revisits the elaborations. There might be an opportunity to put some of that stuff in there too.
Okay, that's all the time we have for questions. So thank you very much, Bruce.